right, it's 9:30, so we'll go ahead and get started. Good morning, and thank you all for joining. I'd like to welcome everybody to week 2 of the 2022 Watershed Wednesdays series. I'm Emily Dekar. I'm the Agricultural Coordinator for the Upper Susquehanna Coalition. Watershed Wednesdays are hosted by the Upper Susquehanna Coalition and the Otsego County Conservation Association. Usually we have Amy Wyant on the line. Today we have Jeff O'Hanley sitting in for her today. These weekly sessions are taking the place of the Upper Susquehanna Watershed Forum for 2022. We'll be holding sessions every Wednesday through November 2nd. The full schedule is up on the screen and is also posted on the website and our Facebook page. You can sign up for email announcements on the USC website under the Watershed Wednesdays tab. So to get things started, our presenters today are Mike Coriat and Ian Geddix. Mike assesses streams and researches stream-related issues for the Delaware County Soil and Water Conservation District. His prior experience in the water resource field includes the research of streambank erosion in the Catskills for Syracuse University, investigation of stream and agricultural-related issues for Otsego County Soil and Water Conservation District, and the design and construction oversight of BMPs for the Watershed Agricultural Council. Mike hails from the Upper Susquehanna Watershed, where he was born, raised, and currently resides. Ian is a stream technician trainee at the Delaware County Soil and Water Conservation District, where he is currently working on an assessment of the Ouleout Creek in the Upper Susquehanna Watershed. Prior to this role, he worked as a New York City Department of Environmental Protection stream program intern for several field seasons. Ian was born and raised in Saugerties, New York, and is a recent graduate of SUNY ESF. Mike and Ian are going to give you an overview of estimating nutrient loads due to streambank erosion. So just a quick reminder for everybody, the sessions are recorded and will be accessible on the USC website to watch at a later date. And you're also welcome to use the Q&A feature during the presentation. However, we'll hold those questions until the end. We will have time to go over any of those questions and get your questions answered at the end. So with that, I'll turn it over to Mike and Ian.
Thanks, Emily. So to give you a little background about how we got into estimating nutrient loads due to streambank erosion, I'll tell you a little bit about the history. So the Delaware County Soil and Water Conservation District, we have a stream program. We work with New York City. We have a contract to manage the streams and rivers that lead to two of New York City's largest reservoirs, the Cannonsville and the Papacton. It's about half the county's surface area that's within that watershed. We have overlapping goals in water quality. And like I said, we manage the streams and rivers. We do a number of stream restoration projects, flooding mitigation projects, and I do a fair amount of assessment to find problems that are related to water quality, mostly relating to streambank erosion and other stream instabilities. So we got started estimating nutrient loads a few years ago during what we call the Moore Project. So there was an area on the west branch of the Delaware River that was laterally eroding quite extensively. A lot of area of hayfields was being eroded. It started out with some deposition, and a tree got lodged and it started diverting the river. So that was first step. We had a very large restoration project to fix that issue. And since then, we found two additional large issues of really severe lateral erosion. And we've been tackling those. So I'm going to relate a lot of this presentation to that project and those case studies. And to give a little more background to, well, why would you estimate nutrient and sediment loads? Well, we sought out to do it to prioritize our projects. So, you could look at a river and break everything into reaches and look at erosion by linear footage. You could look at it by eroded area. You could look at it by volume. We were having to make some tough decisions, and we said, well, what we're really after here, at least in the West Branch Basin, is phosphorus. So why don't we actually look at what amount of phosphorus is making it into the river due to stream bank erosion. You could be doing this for general water quality concerns. In our case, it also relates to the reservoirs. Eutrophication is always an issue that you want to minimize. Obviously, for the USC, this is of interest for the Chesapeake Bay. And just generally, no matter where you are in the state, if this is something you want to do, it can really help give you ammunition for grant funding. Okay, I'm just going to jump right into this. We're going to zip through. I have a lot more content than we can cover here today, so I'm going to try to cover the general outline. If you're more interested in this, we have a technical paper out. It's online. I can also email it to you, or you can ask questions at the end. But anyways, I'm going to jump right in. So this process for estimating nutrient and sediment loads due to stream bank erosion is 3 general steps. You want to measure eroded soil volume. You're going to measure the physical soil properties and soil nutrient concentrations of the soils that are being eroded. And then from that, you can estimate total phosphorus and total nitrogen mass loaded. You could realistically look at any of the nutrients, any of the components that make up total phosphorus or total nitrogen, but regulatory authorities who are concerned about this or who are, parting with funding, those are the 2 main nutrients that they're looking at, essentially, and concerned with. Okay, so when it comes to volume, in our case studies, I use GPS points plotted on ortho imagery to determine eroded area and eroded volume. Realistically, you can use whatever you have at your disposal. You can cater, if you're a district, to your strengths. If your strength is topographic survey, you can do that. Maybe you have a drone that can do survey. You could use that. You could even just do survey cross sections with a laser level and a tape or a dumpy level. You could use bank pins or toe pins to also monitor the erosion. What you just need to actually measure the erosion, how much is being eroded over an amount of time. That is base level, what you're trying to find. You could also use a modeled approach. We'll tell you a little bit more about this, such as the bank assessment for non-point source consequences of sediment. I think I got that right. It's a Roskin model where you take field measurements and you measure length and bank height in the field. And what you're modeling is a lateral erosion rate. And from that, you can get eroded volume as well, or you can combine these approaches. So here's an example of taking GPS points and plotting that on ortho imagery. So each of these orange triangles here is a GPS point, and those are taken at every break in plan form and every break in bank height. So you're essentially just mapping every change in potential volume that is being eroded here. Once you have these, you can connect the dots with a line and then trace the extent. So this is 2016 ortho imagery. You would trace the bank extents, up through, and that gives you your eroded area. You're also taking the bank height at all these GPS points. And from that, you get your 3 dimensions, you get volume. You need a decent GPS. We use a Trimble Geo 7X. That's a 10 centimeter unit. So it gets 10 centimeter accuracy. Sometimes a little better, sometimes a little worse. There's more to do with that too, as far as checking the accuracy. That's a whole different thing we could get into. So that's one way. Here is an example of a bank pin being used. So that's Jessica. She is in our stream program, Jessica Patterson. So that's literally a piece of rebar driven into the bank. You measure where it is when you put it in. You could just get a flush with the bank. You come back after a flow or after a year, and you measure how much is eroded, and that gives you your lateral erosion rate. You could do one in the bank. You can do several in the bank. You can do multiple levels of detail when it comes to that. Toe pin is very similar, but it's driven into the toe of the bank, and you use that as a point to measure off from. Different method. I know Dave Roskin is getting away from the bank pins because that can cause some hydraulics at the bank and maybe increase the amount of erosion that's going on. And I talked about the banks model. Here are the two specific components of it. We have the bank erosion hazard index and near bank stress. So these are two ways to assess what's going on at an eroding bank. So the one is variables that would influence bank erosion. The other, physical characteristics of the bank, and the other is, the influence of the water on the bank. We use methods 1 and 5 to do this pretty much exclusively in the field. Those are really the ones that are applicable in the field. Once you get those, you plot them against each other. Roskin has his own erosion rates based on those measurements you come up with, and you can get your lateral erosion rate, or you can create your own. So the simple rundown here, get your volume, you need your 3 dimensions. So you usually have a square area for the GPS points. You multiply that by the bank height, using metric here, but meter squared times meters, feet squared times feet, you get your units volume. Moving on from that, so you're going to have to convert this all to mass. So how do you convert volume to mass? You need a density. When it comes to soils, you're talking bulk density. So that's just a measure of the soil density, incorporating all the physical factors that go along with it, all the voids, all that good stuff. So you multiply your cubic volume by your bulk density. You have to do your dimensional analysis. You want to be really careful with this. You have to make sure all your units cancel out. This is all metric again, but just an example. So you're going to end up with a mass of soil at the end of this calculation. From this, you have to determine the fine earth fraction, which is just a term for the fraction of the soil, which is less than 2 millimeters in size. So that's sand size and smaller. So all your rock fragments, they're going to be larger than that. They will contain phosphorus, but that's eroding out at a geological timescale. It's not really going to be of interest for your purposes. It's not going to influence water quality on the timescale we're concerned with. So you're going to exclude the rocks, essentially. All the nutrient content should be in that 2 millimeters and finer fraction. So you have to determine that. So like the bulk density, I measured that myself. In the case studies, I'll show you fine earth fraction. I also determined that myself using sieves, sieving that out. But I'll also talk about ways to streamline this and get around that if you don't have the resources or ability. So you take your mass that you just calculated based on the volume and your bulk density, you multiply that by the proportion of the soil that's actually sand size and smaller. And that gives you the fraction of your soil that actually contains the nutrients. After that, you need to sample your soils. So you need to determine the total nitrogen, total phosphorus within them. You want to do this methodically, and in order to do that, what I did is I break it into manageable segments by soil type and land cover. So your soil type, your physical attributes of that are going to vary based on soil type, and your land cover is going to influence your nutrient concentrations. If you're getting manure spread on certain fields, you're going to have higher nutrient concentrations, and you're going to have variances based on whether it's wetland, whether it's in grass, whether it's an herbaceous buffer, a woody buffer. So you gotta, plan for that. What we do is composite samples, sample every 50 feet along a length of erosion, and you make a composite sample, and then you take a subsample from that, ship it to the lab or drop it off, and get it analyzed. You're going to get results back, typically in parts per million or milligrams per kilogram. They do it, there's a couple different ways to show that. But here's an example of how we broke up some of the sampling on the West Branch. So here, this was its own soil sample, a composite, its own composite here. This orange line is the bank erosion, its own composite sample here, one at this wetland, and one over here. So breaking up by soil type and land cover. Here's an example of what it looks like, literally scraping off the bank face and getting a sample in the bucket and mixing it all up after you've taken samples along every 50 feet and then shipping it off to the lab. I want to go back to what we're looking for the cost of samples right now. It's about $130 a sample. So it is an expense. It's not cheap. So you want to plan this out ahead of time and, know what your budget is and how many samples you're doing, what you have to work with. We'll talk about that a little bit too, hopefully. Okay, so once you have your soil mass that's been changed by the proportion of the fines in there, the finer sediment, and you get your concentration back, you multiply those together, and that gives you your estimated mass of phosphorus within that eroded area or volume rather in mass. Again, you got to do your dimensional analysis down here. Got to make sure all your units cancel, but really not too difficult of a calculation. It's the same with nitrogen mass here. Okay. Some assumptions, at least if you're using the GPS overlay or plotting or superimposition. You're assuming constant floodplain elevation. This is if you don't have prior bank heights. You're essentially assuming the bank heights that you capture in the field at the time of your survey or your GPS was what it was at the time of your ortho imagery was taken as well. Related to that, you're assuming a constant stream bed elevation. And also with this, you're assuming that your soil sample is an accurate representation, which you should do your best to make sure it is. And we're going to show you a couple of case studies here. Specifically, I'm going to show you Birdsong Farm. We don't have time for River Haven. So these were two locations on the west branch of the Delaware River near Delancey. So this is a field here that is being eroded. This is 1993. This was the plan form of the river at that time. Fast forward to 2015. What a change. So the plot 1993, the bank extends where it was. Some pretty dramatic erosion going on there. There was a narrow woody buffer at the start of this, and once that eroded away, things really got out of hand. This has been alternating in row crops in hay the past number of years, currently in hay, but just not much holding that bank together. Show you some photos here. This is the apex of the bend, looking downstream, looking upstream. And close up of the bank material, that's greater than 90% sand size and smaller. So, some pretty fine material. If the roots aren't holding it together, the river is just taking it away. So this is 2009 ortho here. So that was where the bank was. And then this line here is where the bank was in 2019. So in a 10-year period, we're looking at over 2 acres lost here. So this is that same eroded area, 2019 bank extent here with 2016 ortho imagery. So since 2016, 2019, this amount was eroded here. And then I'll just show you here what we're getting as far as total phosphorus and total nitrogen. We sampled topsoil and subsoil separately, thinking there would be a difference. Statistically, there was not. There was no statistically significant difference. There's a slight difference if you're looking at these figures, ranges from about 300 to just over 500 parts per million. And with total nitrogen, you're looking at about 1,000 to almost 3,500 parts per million within those soils. Again, slight difference between topsoil and subsoil, but not a statistically significant one. And then we have our totals here. So we're looking at, in a 10-year time period at Birdsong Farm, which I just showed you, over 6 tons of total phosphorus was loaded into the river, and 37 tons of total nitrogen loaded into the river. So some pretty staggering amounts in there. I mean, just the eroded soil mass alone, I mean, you're talking 17,000 tons. It's a lot, but it's, it's 2 acres of soil, about 4 to 5 foot high banks. Giving you a quick idea of the flows here. So around bank full to highs of about a 16-year return interval. So we did get some sizable flows during that time period that we were determining these losses. And to give you a little perspective too, so within this management unit, that section of bank erosion made up 18% of the total linear erosion, but it made up almost 77% of the total eroded area just at that one site. Perspective too, so this all drains to the Kansville Reservoir. It's the main source water. These 2 sites accounted for roughly 2% of the total phosphorus estimated budget for the reservoir. So that's just from 2 sites out of a very large watershed. So it seems like, streambank erosion really is an underestimated contributor to nutrient loads in the watershed. We're hoping to take a closer look at that in the future, the rest of the watershed. And the erosion's been continuing. We're hopefully getting a project on the ground the next couple of years here. But just at Birdsong, over 2.5 tons loaded since 2019, the past 3 years of total phosphorus loading. Okay, so now using this, we're kind of moving forward and applying it to other watersheds. We're applying it, I'm not, but this is being pushed forward by our Susquehanna program into the Ouleout Creek to estimate nutrient and sediment loads due to streambank erosion using a slightly modified approach. So we're using the GPS point, I call superimposing that to get area estimates, in addition to using banks erosion rates, that model I was showing you earlier. Just because the GPS doesn't work everywhere in order to get accurate measurements. Obstruction from trees has a big effect, and then maybe you're just not getting good satellite reception either. We're switching up a little bit. Instead of taking direct measurements of bulk density and particle size, we're using web soil survey. It's not as good as getting direct measurements, but it gets you pretty good estimates and gets you in the ballpark. But we're still sampling nutrient concentrations because you can't estimate that using web soil survey, and it varies far more than these other factors. Okay, now I'm going to turn it over to Ian. He's going to tell you a little bit about how the Ouleout Creek project is going.
All right, thank you. So like Mike mentioned, my main focus is the Ouleout Creek assessment, which is basically modeled after what the work has been done on the west branch of the Delaware River. Some background information. My project and research is funded by the Upper Susquehanna Coalition. The Ouleout's a tributary to Susquehanna. If you look at this map here, the drainage area, it's 109 square miles, so it's a pretty sizable stream there. And the Ouleout watershed contains a substantial amount of ag and such as dairy and crop production. So you would expect to see similar issues like we see along the west branch of the Delaware. Assessment overview: the goal is to identify, prioritize, and remediate water quality issues on the Ouleout Creek. This is going to be accomplished by assessing approximately 20 miles of the main stem of the Ouleout Creek above the East Sydney Dam using stream feature inventory methods. Step after that would be to sample representative stream banks for nutrient content and calculate the nutrient loading rates that Mike walked you through before, and then write action plans for each reach and an overall Ouleout watershed action plan. So a stream feature inventory, this is what the bulk of my work this summer has been. Just going along the stream and doing data collection. So you walk the stream, and stream bank erosion and other stream instabilities and features are documented with a GPS. GPS has a unique SFI dictionary to help you characterize whether, let's say you're taking a bank erosion point, whether it's upstream or downstream, left bank, right bank, the bank material, the height, the bank composition, the failure mechanics, all that stuff. And in addition to being captured with a GPS point, the features are photographed. You'll take notes for each feature, and measurements are taken when applicable, like the height or the bank angle. And also, like Mike mentioned before, for each erosion segment, a bank's assessment is also conducted. Here's some SFI features that we capture. These are just the main ones. There's plenty of others as well. So the 2022 SFI so far, I've assessed about 16 miles of the Ouleout Creek. It's about 1,861 GPS points, about 1,257 bank erosion points. So to put that in perspective, here's the main stem of the Ouleout. Here's all the points I captured. So that's quite a lot. And then here's just the bank erosion points. So when you look at that, it's pretty much continuous along the whole main stem, just bank erosion everywhere. So it's not feasible to sample every erosion segment, whether that's time or the amount or the budget, like Mike mentioned before. So you want to do two things. One, we'll sample the sites of extensive erosion, and two, we'll sample where areas where nutrient concentrations differ. So the question would be, where do nutrient concentrations differ? One would be like by land use and land cover. So a forest versus a crop field. Crop field, you would expect to have much higher nutrient concentrations. And two, soil series would also be where nutrient concentrations differ. So if you look here, we have 25 different combinations along the Ouleout of those land use, land cover, and soil series. So to close this out, I'll show you some sites of substantial erosion that we're looking at. This is one site. It's about 36,000 cubic feet. It's a Barber Trestle cropland classification, and it's eroding into a cornfield. So you can see on this is 2016 ortho imagery, and then the orange is the bank erosion. The current bank line in 2022. Here's what it looks like. You can see eroding right into a cornfield, and also it's also depositing alluvium and cobble and material on the bank. So in addition to losing field to erosion, you're also losing cropland to deposition on top of the bank. Second site is about 139,000 cubic feet eroded since 2016. That's 320 16 cubic yard dump truck loads. So that's a significant amount of material being put into the stream. This is historically an area of lateral adjustment, as you can see by the multiple oxbows within the floodplain. So historically, the channel does shift a lot here. This is what it looked like in 1997, and then that bend right there got cut off by an avulsion and is now flowing there and eroding laterally rightward. Here's a picture of what it looks like. You got a point bar and a grading point bar and some bank erosion on this bend. It's another picture. And future work. So most of my work so far has been along the SFI and data collection. We're currently in the process of collecting soil samples. Samples will be sent and tested for total nitrogen and total phosphorus. Once nutrient concentrations are determined, we'll do the calculations of the volume of eroding bank segments. And then after that, we will write management plans for each completed SFI reach. I think Mike.
Yeah, so I'm just gonna sum some of this up. So you can do this cost effectively. Like I said, you can use the resources you have to measure erosion. You can use web soil survey to get some of these soil characteristics that you need. But in addition, there's not really any getting around the cost of the soil analysis. Okay, so tie it up here and see if anybody has any questions.
All right, well, thank you so much, gentlemen. Really appreciate it. We do have a couple of questions, and I'll just remind people that if you have more questions, you can type them into the Q&A bar. And so first question we have, I have a stream running through my 2-acre property that goes to a large wetland 1/4 mile behind my house. Over the last 30 years, it went from a babbling brook 2 feet wide, 1 foot deep, to a 10-foot wide, 5 to 15-foot deep trench that has water during late winter with snow melt and after major rain events. I am attempting restoration with plantings, but cannot as a homeowner do any major restoration or testing of soil. I am losing approximately 1 foot of land from Streambank each year at this point. Any suggestions for people like me with this situation?
That's a tough one. So what you're getting is a lot of incision there. So the actual stream channel bottom dropped way down. And once that happens, your stream's going to try to adjust itself laterally and like rebuild floodplain oftentimes until it gets back to a stable state. Said it dropped like 5 to 10 feet. That's that's a situation where planting trees unfortunately really isn't going to help you. Unless the trees are falling across the stream and creating some type of stability as far as grade control, ensuring that the bottom isn't going to move any further. But yeah, it's tough. I'm not sure you can do that without any serious intervention.
Okay, thank you. All right. Second question is, how big of an issue does New York State feel this is? We have argued in Pennsylvania that this is a major source of total nitrogen and total phosphorus to the bay, but when grants are handed out, it gets almost no consideration at all. Very little money is put toward this issue. How does New York State treat it?
That's a good question. So we're kind of compartmentalized down here. I know New York City is very concerned about it in relation to the reservoirs. When it comes to the Chesapeake Bay, obviously total phosphorus, total nitrogen is a big concern. My take on it is that the loading of these nutrients due to stream bank erosion has generally been underestimated over the years. And realistically, it probably makes up a pretty large component of, the total load for the river, for the Chesapeake Bay. I mean, you go back to what's traditionally been used, like swap models, any of this modeling that goes into place, they tried to estimate loading due to stream bank erosion, but it's not the best. And they put more of an emphasis on what's running off the landscape while ignoring, the resource concern that's actually in direct contact with your water source, which I think is a mistake.
Okay. Any last questions? I'm not seeing any more. I know it's just a little after 10. I think that's it.
All right. Thank you, everybody. I really appreciate everybody signing in
Wait,
today.
we did get one just came in. What would be considered the phosphorus range in parts per million for a section of stream bank to be remediated?
That's a good question. So your phosphorus concentrations are going to vary spatially. It's going to vary based on your region and what the parent material of the soils are. So around here, we have like a red glacial till that underlies the majority of our soils. And that is just over 200 parts per million total phosphorus. But you're seeing in our ag sections here, it's like over 500 at times. It depends. It's really a way to prioritize. If you can, just juxtapose, if you're looking at two different sites, one's at 200 parts per million and one's at 500, well, you could, that gives you an idea, but you really need to do the math out too to see what, the erosion rates and what is actually being loaded, due to the volume being dumped into your stream. So it varies depending on your region. It's really just a good way to prioritize if you're looking at sites.
Okay, great, thank you. And another question has come in. How much have the upper portions of the watershed changed that may be causing erosion at these sites?
The upper portions of the watershed, so typically our smaller tributaries, they've had some incision problems, like that previous question actually, where the stream bed cuts down and then sets off a cascade of different issues. Some of our tributaries are putting a lot of sediment into our main rivers. And like an example, I didn't go over, but the other site, part of the case study, River Haven, there's a tributary that comes in right where we have really excessive lateral erosion on the west branch. What seems to be happening is that the cobble and gravel load from that tributary is pushing the river over. And, it is having an effect on the dynamics in the river, what's being eroded. You're essentially getting the flow in the river. Is it going to move the cobble or the gravel, or is it going to move the nice alluvium stream bank that's 90% sand size and smaller? It's going to move that nice alluvium a lot easier, and so that's causing some erosion problems too. Everything's connected in the watershed, and problems upstream are going to affect downstream, and potentially downstream is going to affect upstream too. So that's why we do the SFI assessments too. We essentially look at the whole length of a stream, and sometimes we go up the tributaries to get really a holistic look at what's going on in watershed, just because factor issues compound, and what's happening in one area can affect what's happening in a different area too.
Great, thank you. I don't see any other questions. Emily?
Thank you very much, Mike and Ian. I really appreciate it. Just a reminder for everybody, next week we will have another session at 9:30 next Wednesday. It will be Brian Steinmuller from the State Committee talking about the Climate Act. So with that, thanks everybody.
Thank you all.
Thanks for having us.